All right. So welcome. This is a talk on pysparkling. It's a pretty new project of mine. It's a pure Python implementation of Spark's RDB interface. And I'm going to say more what that is. So my background is in particle physics. I wrote statistics tools for CERN, and I was in the core team that discovered the Higgs boson. I always considered myself as a user of data processing tools. So at CERN, we had like custom solutions for that called Proof. We used MPI. At the university, we had like SunGrid engines for batch processing. And also, it was quite handy to develop some like custom SSH scripts if you have like a department of totally different machines, but you want to run large processes on them. So, and then IPython brought IPython parallel with IP clusters. They're nice. And since I left academia, Hadoop and Spark are kind of my platform of choice to work with. So right now, I'm a data scientist at Wildcard. Very exciting week for us. We just launched on Tuesday, and we're the best new app in the App Store. So go download it and check it out. And of course, we are looking to grow our data team now that this has been so successful. So we're looking for smart Python people to join our data engineering team. So for people in the room who know what Spark is and who saw the subtitle, I just want to manage expectation and just completely be clear about what this is not. So you don't substitute pysparkling wherever you use Spark right now. Spark is absolutely great, and you should use it. So anything that is like big data processing, you use your full Spark cluster. Anything that has to do with distributed sorts and kind of joins that you need to do, you use a full Spark cluster. The purpose of pysparkling is to have the same interface, but not applied in the same situation. So a couple of examples. When you have small data, just the kind of data you don't want to spin up an entire Spark cluster. You just have a couple of small files someone gives you on a USB stick. That's where pysparkling is really good for. What we wanted to do at Wildcard was, for example, to write a microservice in Python for our data infrastructure. So we have a large Spark cluster that processes large documents, and we do machine learning and training on them. But then we want to use that classifier in an API endpoint in a microservice. And we need to have some mechanism to apply the same data transformations in this microservice really fast with small resources on this box so that we can parallelize it and scale it up. So we don't want to run Spark on these like little microservice machines. So that's where also pysparkling is going to be good for. Another thing is I had an intern this summer. She was not very comfortable working on a large cluster, so she used pysparkling as a drop-in replacement for everything that we use Spark for, and developed on her local machine. So of course, she was working on much smaller data, but she developed completely new algorithms that we just could scale onto the cluster and had no problem running this. And something else that's kind of, it does it because I wanted it to do, because I needed that. If you have a large data set somewhere, you just want to build like a tool to like spot check your data and make sure it works fine. You also there, if you want to have like either an in-house team or an offshore team to do that task, you just want a little tool that knows about all the data, but at any given time only knows about like one document in your data set. And so pysparkling is also, in that sense, good with large data if you only access a small part of it. So I'm going to show you a few examples where we make use of that. All right. So yes, so use Spark for any large data processing systems, and then pysparkling I see as like kind of the small data solution that very nicely tags onto that. So just kind of to give you an example for what we usually do, we have like, we call it a data pipeline, and on a high level, it looks like this. It actually looks like a pipeline. So you have like some system that just starts with a text file of URLs. You want to scrape these URLs, you want to extract data from it, and you want to output them. That's very linear. You don't need any system for that. That's really trivial to do. But reality is usually much more complicated, where you want to do joins in between. After you scrape the page, you want to do a join of another data set where you have other information about this web page. You want to do random splits, so you can have a training and a test set. You want to have certain failure resolutions that are specific to what happens at certain things. And then your entire pipeline doesn't look as nice and linear anymore. So one example, just to show you here, is like, what happens if suddenly you have like some labeled data set that you need to join in here, and actually it's not even clear whether the key of your data set is a URL, or whether it's the redirected URL, or whether it's a mix of both. And suddenly you end up not having like a nice linear structure, but you end up like one record becomes 10 records because one record is associated with 10 URLs, and you need to join between these two data sets. So you need some system that is more flexible than just doing your linear, like one transformation after the other. And Spark does this very nicely. It visualizes this nicely for you, and you can run it on a large scale. So we wanted something so that we can do the same thing locally, or in a machine with small resources. So to jump right in, pysparkling, the first thing you want to do is read some data from a text file. So similar what you would do in Spark, you have a context, that's your object, everything kind of like gets created from, and you just say you have data in a text file. And because Spark is based on Hadoop, you have the entire Hadoop I/O system behind it, and in Python you don't have this, at least not out of the box. So what you want to do is to be interface compatible with Spark. You want to be able to do all of this. You want to say, oh, I have a text file, it's local here. So my intern would do that. But when I run this, I say, oh, this file is actually on some like S3 bucket. And I just want to, on the command line, give to my Python script, it's on an S3 bucket. So to pysparkling, I can just give it text files. They are wherever. They are local. They are HTTP connections. They're on S3 or they're on HDFS. And they can be compressed. Your data should not, you should not worry about as a data scientist whether you read in compressed files or not. So this is just transparent to the user here when you read in these text files. Another thing that Spark comes with, so pysparkling should also come with this, is it doesn't make a difference whether it's one text file or you comma separate list of text files. And it doesn't make a difference whether you say you have an entire directory of text files and you just say, with question marks and star wildcards, you just get all of them. So that's what comes in Spark, and that's what's also in pysparkling. So it also exposes these underlying operations that it does there in its own object. So if you want to write something else, so we have classifiers that we read in that is not part of the normal Spark interface. So when we read now files in, just plain files that are pickle files or whatever, we just use the underlying file I/O object. So there's a binary file object and there's a text file object. And we can give it just any location with any compression, and we read these files. So to give you an example, because I think not everyone is too familiar with Spark itself, this is how it works in Spark, and this is how it works in pysparkling as well. So this is just like a little tutorial on Spark. You create a context, as I said, and to create one of these data sets, they're called resilient distributed data sets. This resilient and distributed part is not entirely true for pysparkling, but this is what they're called in Spark. So you say you parallelize like a list of 100 numbers, and you want them to be 20 partitions. So any kind of parallel processing framework, you always have to kind of specify how do you want to partition your data. And usually, if you know your data, then it's actually quite obvious what your partition sizes should be. So here we just say 20 numbers at a time, or sorry, the 100 numbers should be divided into 20 batches. So this is how you create your data set initially. What you then can do is you can apply, for example, a function to every element of the data set. So now we just say add the number 10 to every number in the data set. And at this point, nothing has happened. So all operations are lazy in Spark and in pysparkling. And so nothing was executed at this step. The next thing you can do is you can say you want to cache this output because the computation before was really expensive, which here was not the case, but it might be. And then you can do operations that are collect, which would mean you read the entire data set, or you can say first, and you just want the first element. There's also operations for take a random element or take 10 random elements in the Spark API. So what we do here is we just say, get me the first element. And then at this point, it's the first thing that something actually happens. So at this point, it knows the first element is in the first partition of the data. So now it goes back. It actually executes or computes the first partition, so it adds 10 to just the numbers in the first partition. Then it caches just the first partition, and then it returns the first element of the first partition. So nothing else is computed here. So if you have a huge data set, and you just want a first or a random element, it just operates on one partition. OK. Please ask questions if that's not quite clear. One thing that I should probably mention here, why is the syntax so weird? That you assign RDD equals RDD.map. So RDDs are also immutable. So although they're not executed immediately, Spark, in its way of computing, creates new RDDs all the time. They're just not computed very often. So, but in the way how to think about it is every RDD itself is immutable. All right, so as a machine learner, you might want to do some exercise in how to compute something. So this is a confusion matrix. Is you have a data set that has like actual labels, cats, dogs, and rabbits. And you build a classifier that predicts what your sample is. It might be a picture, it might be a text document describing a cat, a dog, or a rabbit. And a confusion matrix is a table that just gives you the counts of like how often it was an actual cat and how often it was predicted to be a cat, how often it was an actual dog, and how often it was predicted to be a cat. So it's just a way of counting how good your classifier performed. So what you can do in this setup here is you can you get these pairs after you processed and applied your classifier distributedly on your cluster. This is usually the computationally expensive step. You did all these predictions for your entire data set, and then you have pairs of like a predicted class label and a true class label. The class labels here are just numbers, 1 and 2. And you build a confusion matrix from that. So a table like this, just for this one record, you say this is what this table would look like. Once you would have this table, you can derive all your standard like performance measures, precision, recall, support, and F-score just from this table. And the table is very small, but to apply this and get it from a data set is very large. So we have a demos IPython notebook in the repository. This is how it could look like. For this specific case of only having one classification per entity, it can actually be simplified a bit. But this is about what it looked like. You parallelize your fake data here. This is like these true and predicted labels. And you use one of these Spark functions that's called an aggregate, which you have to give a 0 value. So this is the initial form of your confusion matrix. It's just zeros in a 3x3 array. And then you apply sequence operations on it. These are take the previous confusion matrix and add the confusion matrix per this pair, per one of the elements. And this is just one of these confusion matrices that I was drawing before. So this is just this step. You create a confusion matrix from this, and you add it to the previous one, and you add it to the previous one, and you add it to the previous one. In a distributed setting, you actually do this on several partitions in parallel. So you, at the end of your sequence operations, you want to combine the result of all the operations per partition. So you have to specify what you want to do with that. So in NumPy, you can just add two arrays. One other thing that is kind of experimental and was more like a why not do that instead of like stop here. Once you have this interface, of course in Spark it's used to actually do large-scale distributed computing. So the interface here would look like this if you want to do parallel processing with pysparkling. To run it on your local machine, if you have a machine with a couple of cores, you can use the multiprocessing module from Python. And you just say you have a pool object. And the pysparkling context is written such that it can take any pool object that has a map function. So you can say you have 7 cores in your computer, or you want to use 7 of your whatever cores in your computer for this. You specify a method to serialize your transformations, your map functions, whatever you want. Cloud Pickle is a little bit nicer than Pickle. It can like serialize Lambda functions, things like that. And then you deserialize your functions again. So one nice thing that's built in is that maps are chained. So if you have your RDD and you apply like one transformation after the other, when it gets executed, it executes all the RDD or the maps in one long chain. So it doesn't continuously like parallelize the process, aggregate it, parallelize it, aggregate it. So it just sees that there's a lot of map operations onto the same partition and like executes them all in a row. That might lead to some problems with caching, but that's also handled here. So if you have any intermediate steps on your worker nodes that need to be cached, pysparkling takes care of it and distributes the cache as it needs to. There are other pool objects that I played around with. So the new futures thread pool executor, or even an IP cluster. IP cluster has a view object that also has a map method, so you can actually distribute it across a small cluster. One caveat here is, and that's why it's still very different from the actual Spark, the only thing that these underlying parallel processing systems parallelize is map functions. So Spark has wonderful distributed shuffle operations, sort operations, and join operations, where, just these pool objects that I've so far looked at don't do that. And I actually don't know of any that do that. So that's kind of technically what I have to say about pysparkling. I just wanted to point out that there is some documentation, so have a look at the code or these documentations. So these are automatically generated from the code, and they're unit checked with every code commit. So there's some examples embedded into this documentation, and they're guaranteed to run every time. So you have this long list of all the Spark operations on these data sets. And you have the link there, so I hope this will work when we share the slides. And then there's also a demo IPython notebook that has like a standard word code example, how it is done in Spark and how it's done in pysparkling. So that's it. As I mentioned, there's no really any external dependencies unless you want to access some of these external file systems. So you have to specify these dependencies. If you want to access S3, you have to say it here. Or if you want to access HDFS and HTTP. So yeah, there's all the references that you need. That's it. I use it in production, so hopefully I will be committed for quite a while to keep that in sync. The actual API of Spark, I think is stabilizing pretty quickly now. So it's kind of, I have very high respect for these people who invented this because this is like a really solid, nice interface to work with data. And I think there's been a lot of thought into what interfaces to expose to the user. So I'm not too worried that they've changed dramatically over a long period of time. So. That's a good question. I don't know that. Sure. Am I the one picking people? Okay. Right. I think you were first. Okay, sorry.
So how much of PySpark is supported over here? I took a quick look. Are you supporting Spark SQL, data frames? I don't think MLlib is in there at all.
This is the RDD interface so far. So. 90-something%. Yeah. I consider that a bug if it's not, but there are some bugs. So there's some functions that are like zip with index or something like that is not in there. Yeah. Let me know if you need one of those that are one of the few functions. Then it's very easy to do this. Yeah. If anyone wants to have a look at the code, it's usually like the initial thing for pysparkling is when you look at it, it's like, oh, this is for loops. Once you want to do it lazy, and once you want to have all this access with map partitions and then want to parallelize it, it's not that simple. But a lot of these functions that are currently implemented in RDDs are 3 lines or so. So it should be very easy to implement the rest. Yes, you were first.
That was my exact question.
Okay. All right. Sorry. We don't have anyone remotely currently. We are on Grant Street.
I'll go for another question.
Sure.
I guess what's the data size cutoff you found in practice from kind of using pysparkling versus pyspark?
That's a very good question. I'm not sure I have found a cutoff. So the last version, version 0.3, we released on Friday. So I don't think I've pushed it yet so that it would actually cut off. It's just, there's just some operations once you think about it, if you have, I don't know, a couple of terabytes of processing, it just seems wrong to do it. But yeah, I mean, people have, I don't know how people have pushed IP clusters. So I guess that's kind of the biggest scale that currently, I think that's IP clusters, and I don't know how people have pushed it.